Boom. The first thing we're going to do is we're going to see what happens when we do the following. We're going to simplify with everyone's favorite F word, fractions in the exponent. And I'm hearing you say, what? There we go. That's what we're going to do. First thing we're going to do. The only thing you need to know when dealing with these things is all the laws still work normally. Okay? Nothing has changed. And so in the past, what I would do is I would give students, like I didn't actually do a lesson on simplifying with fractions in the exponent. I would just give them, and my students were like, what is this? And like, well, they're just numbers. Just do them the way you would do them. I don't know what a fraction is. What do you mean you don't know what a fraction is? We spend the entire first chapter doing math with fractions. So, we're going to bring it back here. And we're just going to do a couple examples and make sure we're all on the same page here. So, first example, here we go, write this down. X to the negative 3 over 2 in brackets, and we're going to cube that. We're going to times that by x to the negative 3 over 2 over x squared times x to the negative 3. So now we've got fractions going on in there, but the laws work exactly like we would expect the laws to work. Nothing changes. You just have to make sure that you're doing the algebra the appropriate way. Or sorry, not even algebra, the arithmetic the appropriate way when dealing with fractions. So, who wants to take a guess or tell me what they want to see me do first? Kyla. Sorry? So you want me to, so I've got a power to a power here, you want me to distribute this thing in. Okay? So if I do that, what do I get? How do I, okay? So we got to make sure we multiply whole numbers and fractions together properly. We've got a power to a power, so we multiply. When I have a fraction times a whole number, what do I do? 9 over 2, negative 9 over 2 is correct, to those of you who said that. But how did you do it? But how do you multiply a fraction by a whole number? What do we do? Put the whole number over 1. Multiply the numerators and the denominators. Cool. So this is going to give me x to the negative 9 over 2 times x to the negative 3 over 2 over x squared times x to the negative 3. Sorry? So you can start moving the negatives and positives around if you want. You're welcome to do that. But is there something that perhaps we could do before we move anything around? Case 10 meet. So the bases are the same. Add what? So I'm going to add the exponents. Because I'm multiplying the same base, I'm going to add the exponents. I can do that in the numerator, and I can do that in the denominator. Okay, so if I do that, what do I get? How do I add those fractions together? Harwin. You said times? And so, but how do I add fractions? And do they have a common denominator? Yeah, so then what do I do? Yeah, so when you have a common denominator and you're adding, you just add across the top and you leave the denominators alone. So negative 9 plus negative 3 is? That students become negative 12 over 2. Over, and then we can do the bottom right away. What's that going to be? X to the power of negative 1, you betcha. So you can see here the rules aren't changing. We just have to make sure that we're dealing with the fractions properly. So what can I do next? You want to flip them? Because I've got a negative in the denominator, negative exponent in the denominator, and a negative exponent in the numerator. Is there something I can do before, as I do that, like kind of in the same step, just to make my life a little easier? Presley, I saw that hand.
Can you add 1 to this division, so you would minus -1, which is adding 1.
Oh, you want to do the subtraction here?
Yeah.
Is there some easier thing we can do before that? Carolyn. Negative 12 over 2 is negative 6. So let's do that. That's going to give me x to the negative 6 over x to the negative 1. Let's be careful here. Those are the same base. So before we do any flipping, let's actually make sure we can group them properly. I like Presley's suggestion is what I would do. It's not what you have to do, but it's what I would do. If I got x to the negative 6 over x to the negative 1, when you divide the same base, we subtract exponents. Negative 6 minus negative 1 is the same thing as negative 6 plus 1. So that's going to give me x to the negative 5. And when you do that subtraction, it starts in the numerator. But because we know it's going to be negative, we can drop it down to the denominator right away. So what's my answer going to be? 1 over x to the 5. Cool. Comments, questions, concerns, any piece of that? Makes sense, yes? Let's do one more example. Oh, yes, Carolyn. Yeah, that's what Harwin was really pushing for. Yeah, there was a few people who were going to suggest that. That is another option. It wouldn't be ultimately incorrect, but I was running out of space on my paper, and so I didn't want to do that. It was really, that's the only reason I didn't want to do that. Here we go, another example. We're going to do m to the 5 over 4 times m. Now, what would be a really good kind of mean example to give you guys here? What do you think might be good?
1 over 2.
Why 1 over 2?
Because that's too small.
But that's easy. That's easy. The thing I didn't say that. The thing I want to demonstrate a particular skill here. The top one, I had these denominators were the same.
1 over 3 giving us
Actually, the number I had was 2 over 3. But that's the idea, right? Because we can see here what's going on. Now, what do we do when we've got, different exponents, different exponential bases, different denominators in the exponent for the same base? What do we do with that? And this is going to be over m to the negative 2 over 3 in brackets to the negative 2. Okay, Carolyn, I see that hand first. Okay, so because I'm multiplying the same base here, I want to add the exponents in the denominator. To add fractions, I want to add, words are hard. I want to add these exponents, and to add these fractional exponents, I need a common denominator. Carolyn suggested 12, because 12 is the smallest number that 3 and 4 both go into. Works for me. To do that, I'm going to multiply the top and bottom on this fraction by, I'm going to multiply top and bottom on this fraction by, so now I can rewrite this thing. Oh, and while we're doing this, I'm just going to bring the party in down here. Going to do it all in one step. This first m is going to be to the power of what? Sorry, I heard something. 15 over 12, good. The second m is going to be 8 over 12, good. Over, what's my bottom one? Be 4 over 3, good. Because this negative 2 becomes negative 2 over 1. When now on the bottom, I'm multiplying the fractions. Negative 2 times negative 2 is 4. 3 times 1 is 3. Cool. Who wants to take next step? Hand meet. I saw that hand first.
you can add the fraction in the numerator.
Okay, what's that going to give me? Yeah, what's that going to give me? I heard it, 23 over 12 over m to the 4/3. What's my next step here? Harwin, you have a question?
For 4 over 3 to subtract something
We're subtracting now. Why are we subtracting? Because it's division, so I need a common denominator here. Common denominator of 12 and 3 is? It's 12. So how do I... I see that hand.
Leave the top the same, like m to multiply the 4 by 4.
So I'm going to multiply the bottom fraction, top and bottom, by 4. And so that's going to give me m to the 23 over 12 over m to the 16 over 12. And now I can subtract 23 over 12 minus 16 over 12 is? M to the 7 over 12, and we're done. If we could, yes. Absolutely. If you can, absolutely reduce. Is this reducible? No. So we're done. But let's make a note here, because Harwin, that's a good thing to bring up. Reduce all fractions where possible. In final answer. And now you guys are going to have calculators at your disposal, so that should become real easy to do. Especially if you have the Casios, because it'll do it the actual reduction for you. It's pretty sweet. Okay. We cool? Yes. Here? So I multiplied 4 to the numerator and denominator because Harwin and Danny both said that we're going to have to subtract exponents here. So when you subtract exponents, you need a common denominator. So the denominator here is 12, and the denominator here was 3. The smallest number that 12 and 3 both go into is 12. So we multiplied top and bottom on this fraction by 4. And that's where we got 16 over 12, and then we subtracted. Nice and easy, yes? Okay, so nothing changes. You just need to be comfortable with your fractional algebra, or fractional arithmetic, I'll say. Flip the page. Next one. Yes, Kyla. How much room do you have? If you have more than half the page available to you, then write it however you're going to write it. I had less than half the page. Yes, if you got more than half, basically everything, I'm going to do 1, 2, 3, 4 more things. As long as you're, with each one, as long as you have more than half the page available to you, you don't have to flip, but I'm going to flip. They all build on each other. So they're all related, but they are all a little bit different. So the next one we're going to look at is converting fractional exponents to Presley. What am I going to convert them to? Rebecca, have you seen in your extracurricular mathematical activities? Sorry? That would be what you'd think, but no. Carolyn, have you seen this back home? Okay, here we go. So converting fractional exponents to radicals. I knew it. I knew it. I knew it. So I knew at least some of you had seen it. Okay, so the question is, what the heck is a radical? And this is not a cool word out of the 60s. Does anyone know what a radical is? It's a trick question because you all know what radicals are. You just have never heard them called radicals before. Radicals is another word. It's a mathematical term for roots. Yes, but I'm not going to. I'm teaching you new vocabulary. Welcome to the language of math with Mr. Dweedoff. So, radicals is just another way to say roots. So this is it's square, roots, cube, roots, fourth, fifth, etc. The family of roots is called the radicals. Why? I don't know. They just are. It's like, why is my family the Dweedoffs? I don't know. Actually, I do know. But, we just are. We are the Dweedoffs because my last name used to be Davidoff. But my so in Russian, all of the last names sons are named like son of the father. Ov means son of. So like Davidov, there would have been a David somewhere in the past. And so the Davidovs mean I'm the son of David. And women are all named Ova. The last name is Ova. So like me and my sister would have different last names. And women's last names come from the mother. So they are daughter of their mother. But my great-grandfather was sick of losing his mail because there were so many John Davidoffs around. So he changed it. He's like, it's not Davidoff anymore. It's Dweedoff. Because there weren't any. So he invented a last name. So if you meet a Dweedoff, they're like almost certainly related to me unless they were adopted or married in. Anyway, so I do know where my last name comes from, but it's radicals. So how do we actually do this? Let's take a look. What if I have this? And all sorts of different last names have different meanings, especially if you're British. Because the British are the easy ones because they're all English things. Like if your last name is Cooper, means you come from a family of blacksmiths. Oh, maybe it's shoemakers then. Anyway, you get the idea. Okay, so if I have this, and that shouldn't be m over 2, it should be m over n. X to the m over n. I'm getting distracted talking about names. What we're going to do here, if I got x to the m over n, this thing gets converted into a radical that looks like this. The whole number in the number in the numerator rather becomes a whole numbered exponent. So if I have x to the m, that's just going to be x to the m. If I have x to the m over n, the m stays as a whole number exponent, and the n goes right there. It gets a name. This thing here is called the index, and the m just stays as an exponent. And it's important to recognize that these two things are the same. The one that I've written, and how I would read this is the nth root of x to the m. This is the same as, because roots and exponents are a part of the same family, like multiplication and division are. They can be done in either order, whichever order is the most convenient. That means we can write it like this as well. X, or the nth root of x, the nth root of x to the power of m. So it doesn't matter if my exponent is inside or outside the radical. Whichever one you're going to do first is, oh hey, what's that? The one that you're going to do first is the one that makes the most convenient sense based on the question that you're given. So let's do a couple examples. Sorry? Oh yeah. Not those ones, but yeah. I see that hand, Carolyn. No, I don't see a hand. Okay, never mind. Here we go. Example. What if I have this? I have 4 to the 1 over 2. What does that mean? 4 to the power of 1/2. So what we're going to do is we're going to convert that thing to a radical. Harwin, you want to do it? Sure. Radical sign now. Yeah, you put the base in there. In this case, the numerator is 1. Do I ever have to write the exponent of 1? But 2 is going to go where? Yeah, in that little slot right there. So what am I actually looking for when I have 4 to the 1/2? I'm looking for the square root of 4, which is, and now we're done. Easy, right? Let's make it more entertaining, shall we? No, no, no. No. Whoa. Timeout. Bad. Okay, now we're doing another example. Back up a page. Okay, now I've got 9 to the 1/2. We're jumping back up over here because I want to fix what I just heard back here. 4 to the power of 1/2. And what I heard, the problem with what I heard was, oh yeah, it makes sense because half of 4 is 2. That is not what we're doing here. Okay? So now I've got 9 to the power of 1/2. What do? Who said that it makes sense because it's a half? Okay, this is your question, Aminette. I'm calling you out. Here we go. 9 to the 1/2. What do we do?
9 goes inside the radical.
Yep.
And 2 goes in like the little slot.
Where the index goes, yep.
And then you don't have to write the 1.
Correct, because I don't have to write the exponent of 1 ever.
So that would be the square root of 9.
Which is?
81.
The square of 9 is 81. The square root of 9 is? So it has nothing to do with the fact that half of 4 is 2. It has everything to do with the fact that we're looking for the square root. So does that make sense?
Yeah.
Okay, you understand why I jumped all over what you said?
Yeah.
Okay, Danny.
Where would the 1 be?
Either here or here.
Yeah, but it doesn't matter.
Because the exponent of 1 doesn't change anything. 9 to the 1 is just 9, or 4 to the 1 is just 4.
An example, is that the same thing? Statement? I missed it. If the m is right there, then
Yeah, it doesn't matter if you put, because radicals and exponents are part of the same mathematical family, it doesn't matter which one you do first.
or which way you write it?
So if you want to do, so on this one, if we were going to do this one, putting the m inside means I'm going to do the exponent first and then I'm going to take the root. Writing it like this means I'm going to take the root first and then I'm going to put it to the power of an exponent. So that's what we're doing down here. This next example here, what if I have this? 8 to the 4/3.
Is it accounted?
Of course it is. Carolyn. Okay, so I have the cube root of 8. Now, Carolyn, where did you want to put the exponent 4? Do you want to put it inside the radical or outside the radical?
Inside, because I don't know the, I also know the cube root, so outside.
Okay, so Carolyn's making a choice here. She's putting the exponent of 4 on the outside because we know what the cube root of 8 is, so that's the easier one to evaluate first. What's the cube root of 8? Harwin. Correct. Kyla. It changes the order you do the arithmetic, yes. So if I put if I put the 4 inside, I would have to do 8 to the power of 4 first. And I don't know what that is. That's 64 times 64. Actually, I could do it in my head if I want. It's going to get big though. 60 times 60 is 3,600. Yeah. I don't want to do that. And then you'd have to take the cube root of that. That just sounds less fun. Where I could cube root 8 really easily. What's the cube root of 8? Someone already said it. It's 2. So this is going to become 2 to the 4th, like I think it was Aminette or Tenmi, one of you two of you said it. And then 2 to the 4th is easy. 2 to the 4th is? And we're done. But did you know that the cube root of, what was the number? 3,600 and, no, 4,096. Did you know that the cube root of 4,096 was 16? No, neither did I. But you know what the cube root of 8 is, and you know what 2 to the 4 is. 16. Because the cube root of 8 is 2. Because 2 times 2 times 2 is 8. Okay. What do I do? Sure, Harwin. Let's do it. I love that you're attempting this one, but do take a look very closely at what's there. What is different from this one than there was in the previous one? There's a negative. So what are you going to do? Ah, careful. A negative in the exponent means what gets flipped? No. What gets flipped when I have a negative in the exponent? We want to get rid of the negative, and we get rid of the negative by flipping not the exponent, we flip the base. So this is going to become 1 over 5 to the 3 over 2. Yeah, and this is what we did. This was a lesson from last Thursday. Negative exponents. Harwin, you still want to continue? Okay. So it'll be 1 over the radical sign, yeah. So the question is, where are we going to put the 3? Carolyn? Because I don't know what the square root of 5 is, because there is no, 5 is not a perfect square. So the only thing we can do to the 5 then is the other exponent, so that's why we're going to put that inside. Generally, yes. So then what is my last step going to be here? The square root of 125. And that is my final answer, because 125 is not a perfect square, so we're done. What I could get, I'm not going to get into decimals, but what we could do is we could simplify the radical. Oh, we've done that already too. I'm going to switch colors here. We don't remember, but that's okay. We can do it anyway. It's still going to be 1 over, but 125 is really big. Could I break 125 up into things that I can take the square root of? Do the factor tree thing, yeah, I could do that. So 125 can be broken up into 5 and 25. And actually, I'm going to stop it right here because 25 is a perfect square. So what I'm going to have here is I'm going to have the square root of 25 times the square root of 5. And the square root of 25 is just 5, so it's going to be 1 over 5 root 5. If I wanted to, connect it to the stuff that we did last chapter, I could. It depends on the instructions that you're given. There's a very real possibility. See, it all connects. And some of you hate that it all connects, but it all connects. Okay. Questions about converting fractions to radicals? Okay. The next one we're going to do is easy, I think. But it's going to connect something else that we've done to something new. I have space, so I'm just sliding down. Because this one, this one's not actually very long. So I can do it with the space that I have. Decimal exponents. Two radicals. Decimal exponents to radicals are easy. Because we don't want to do them. What we're going to do instead is, what do you think we're going to do? We're going to make it a fraction. We're going to decimal exponent is going to become a fractional exponent. And then that thing is going to become a radical. So let's do a nice easy one to make our life, better. I want, example, 16 to the 0.25. Carolyn. Yeah, 0.25 is what as a fraction? It's a quarter, so it's 1 over 4. Which is going to become, sure, Carolyn, keep going. Become the 4th root of 16, which is just going to be, I'm seeing some fingers popping up all over the place, 2. Easy, yeah? Okay, but what if I gave you something a little bit more gross? I want eight to the 0.2. Someone else. Rebecca. 0.2 is 1 over 5. Good. So it's going to become 8 to the 1/5. And then my last step, Rebecca? Five in the index, good. And can I do the 5th root of 8? Does 8 have a nice, easy 5th root? No, so we're done. That's it. One more. Ten to the negative 0.6 repeating. Sorry? Oh, so you want to make it like this? 1 over 10 to the 0.6 repeating? Sure, we can do that. Get rid of that negative in the exponent. Love it. What's next? Keep going, Kyla. You betcha we do. So it's going to be 1 over 10 to the 2/3. So where it's important to know your fractions. That's 10 to the 2/3. Okay. What now? Kyla, do you want to keep going? Why not? Let's keep going. Kyla, this is your question.
Okay, you put 1 over the reciprocal of 10.
Reciprocal means I flipped something.
Oh,
The radical? Is that what you want? You want a radical, and you want me to put a 10 in there.
and then you want to put a 3 where the index goes?
3 where the index goes. And do you want the 2 inside or outside? Why? You've got a couple phone a friends if you want to use them. Nika's No, 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 like, no, Kai, like, there's a couple hands behind you. Nika put her hand up. Carolyn put her hand up. Nika, it's yours. Your hand was first. Yeah, 10's not a perfect cube, so let's put the square inside. Absolutely. So then this is going to become what? Nika, finish it off. No, it's 100. You're right. It's 100. So the radical stays where it is. It's a cube root. And I just do the exponent on the 10. 10 squared is 100. And we're done. That's it. I'm not going to ask you to simplify the radical. Because if I'm not mistaken, this one doesn't have... I'm not going to ask you to do it because I know this one can't be done. Because the prime factorization is going to be 2 times 2 times 4. Oh, maybe no, it totally is. No, it'll be 2 times 2 times 5 times 5. And then we're stuck. So I'm not going to ask you to do it here. Okay. Oh, we're almost done. How many of you are exhausted? These last two are really easy. It was. But this one is easy. Okay, so I just want to make sure that you're comfortable going the other way. This is the thing that we're going to speed this up a little bit here because we can. If I have this or this, what do we have? 10 mean I see that hand. That's it. That. Kyle, let's say it louder. What did I write about? Or was it Angel? Okay, Angel. I haven't heard from you today. Why did I write both? Because these two are equivalent, Harwin, and I want to make sure that you've seen, we keep in mind these two are the same, but you're going to see both, so I wrote them together. They're both equal to this. That's why I wrote both. Okay, so an easy one here. What if I gave you something like this? I'll do two. First example. What's that? As a fractional exponent. Yeah, Harwin? Ooh. When there's no index written, what's the number in the index? It's a 2. Because it's a square root. So this is going to be what, Harwin? Love it. 8 to the 3 over 2. Nailed it. One more. Carolyn. And then finish. There's one more step. Careful. There you go.
Would you want to feel this first, or what if it just makes sense in your head? Can we just do n the power of negative squared?
If you can go straight from here to here, you better make sure this is correct. Because I can't give you part marks if I don't see the middle. But ultimately on something, this is a relatively simple question. There's not a lot of work to show. Just don't screw it up if you're going straight from the beginning to the end. I need to make sure I know what time this class actually ends today because we've got the weird schedule. Class ends today at 10 o'clock. Cool. Carmen. Sorry? The negative comes from the fact, so it was in the denominator. And so just to write it as to remove the fraction, Carolyn chose to write it like this, n to the negative 1/2. You could have left it like this and just left this as 1 over n to the 1/2. That would have been acceptable too. Because you took it from the denominator and she moved it back. She was positive in the denominator, so she puts it in the numerator and then the exponent becomes negative. It might be, depending on the instructions and depending on the question, it might be useful to you do what you did. Okay, last one. Here we go. The thing that y'all like to do. Evaluating. What does it mean to evaluate? Solve the math. Someone said standard form. You betcha. Do the operations. I don't care how you think about it. Not always. I don't assume anything's common sense anymore. I've seen enough craziness. I assume nothing is common. It's common sense not to invade Ukraine, but here we are. So, example. We're going to do 2. What is it? Who wants to do it? Ah, yes, sit up. I see that hand. No. You picked the absolute worst time to stretch. Here we go. I'm just so excited when I see a hand go up in that back left corner because I never see a hand go up in that back left corner. Sujap, let's do it. Put the 27 in the radical, yeah. Hey, shh, up front. Sujap, keep going. Yeah, in the index. Do you want in or out? Why? That is the better choice. I just want to affirm that. You made the right call, but why is that the better choice? Because it's a perfect cube. Thank you to whoever fed her that answer. I saw a few heads lean in. I'm not sure which head it was that ultimately said that. Okay, so, do you want to keep going, Sujap, or do you want to hand it off? To you pick who back there you're going to hand it off to. Whoever told you that 27 was a perfect cube. Whoever said that is who's going to keep going. Nika. Yeah, no, you're good. Yes, it is. No, you're Nika, you're right. So, okay, and this is something I saw that it's something that came up on the test. When you do the cube root of 27, the answer is just, it's just 3. The radical sign goes away because you've done the operation. I saw a bunch of you, you're still writing, like you said, the square root of 9 is equal to the square root of 3. That's not true. Because once you do the square root, the radical goes away. Square root of 9 is just 3. The cube root of 27 is just 3. But then I still have that exponent to the 4 on the outside there. So the Nika 3 to the 4 is? Is 81, you betcha. And we're done. One more. Okay. Who wants to tackle this beast? It's not actually a beast. It's friendly-ish. Carolyn, you've done a lot today. Yes, sir. Let's do it. Oh, come on, Gavin. Okay. What do you think? Okay, give me a first step. Do one step, and then you can hand it off if you want. Okay. You could. You could. What do you want me to do with the 0.5? Distribute, okay? That is a better first step, you betcha. That is a negative 0.5, yeah. So that's going to be 49 to the negative 0.5. What's 4 times negative 0.5? No, this is still Gavin's, because this is still his operation. What is 4 times negative 0.5? It's negative 2, good. Okay, you want to hand it off or you want to keep going? Okay, let's do it. What's next? You sure? There's one thing you want to do before you start throwing down radicals. You don't want to deal with radicals with negative exponents. So how are we going to get those things positive? We're going to flip it. So it's going to become 1 over 49 to the 0.5 x squared. Want to keep going? You said a radical sign. Let's do that. So it's going to become 1 over the radical sign. What's going on there?
49.
Hold on. Carolyn's done an awful lot today. I know Carolyn knows this. You're missing something here, Gavin. I'm not letting you give away up halfway through a step. What's no I? There's something I just haven't written on the bottom here yet. Yeah, the x squared, it comes along to the party, absolutely. It's outside the radical because my decimal exponent is only on the 49, which is why I drew this little line downwards from the top here on my radical. That to me signifies that the radical has been completed. Everything past that is not part of the radical. So we just draw a little bit of a down. Now, 0.5 is what as a fraction? So it's 1 over 2. So this is just going to be a nice square root, right? So Gavin, you can totally finish this. Put the 2 in the index. So then what's the square root of 49, Gavin? So this is going to become 1 over 7x squared, and we're done. See, you didn't have to hand it off to Carolyn. Comments, questions, concerns on any part of this? Okay. You betcha, because if I flip the page, the party starts. Just because you don't think the party's fun doesn't mean someone doesn't think the party's fun. And basically what I'm doing here is I'm just dragging you all kicking and screaming to my party. You have no choice. I'm driving this bus. Bus is going to Party Town. Okay, so There are many questions. There are 100 questions. Okay, no, this is for today. This is for today. No, we're not doing them all. I have never assigned all of anything. Okay? So what I'm going to give you I'm going to dial it down a little bit here. Oh no, I'm not going to dial it down apparently. Oh, yes, I'm going to, no. Because there's some really good ones I want you to do. Okay, here's what you're going to do. From numbers 1 to 36, from 1 to 36, I want you to do every fourth one. Yeah. So you don't do 1, 2, 3, but you can do 4. You don't have to do 5, 6, or 7, but you gotta do 8. You don't do 9, 10, 11, but you gotta do 12. Okay? 1 to 36 every fourth. And then you're gonna do 37. And then you're gonna go 37 to 100 evens. Yeah, it's in there. Then you didn't put it in. But can't start at 19. Okay, let's take a look. Some of you have this, yes? Some of you when you stapled it, when you put it together in the right order. Okay. Oh. That's fun. Yeah. It sucks. Because I gave it to you in the right order. I gave it to you in the right order, so reorganize it. If you don't actually have it anywhere in there, okay, here, let's do it this way. Frickin' heck, these guys. Because I agree with you. Oh, I found it. Here is, if you're out of order and confused about it, here is one that is in order.
I think I found it right.
It'll be on the back desk. If you need to reorder yours, use this as the master. That sucks. That means you flipped
my
it.
entire thing is
When you put it together, it means you flipped it. So Carmen, the page has got to be in there. Go take a look at the master on the back there. You've got till 9:57 to work on all of this, and I'm happy to help. At 9:57. Yeah.
And then the next one starts at 55.
Yeah, we have like negative 2.
Oh yeah, negative time. I like it. That's new. Negative time. Maybe it's, assume, okay, then 9:55. Assume things are changing at 9:55.